The Big Freeze. This is the ending most scientists currently favor. The universe is expanding, and that expansion is speeding up, pushed by a mysterious pressure called dark energy, a kind of anti-gravity woven into empty space. If it keeps behaving the way it does today, galaxies drift ever further apart, stars slowly burn through their fuel, and no new stars form to replace them. Over enormous stretches of time, the last embers go out, and the cosmos settles into a thin, cold, evenly spread haze. Physicists call this maximum entropy, which is just a way of saying everything has run down to the same lukewarm state, with no differences left to power anything. Nothing explodes, and nothing collapses. The universe doesn't end in a bang. It grows dark, quiet, and cold, and stays that way. Cosmic isolation. Long before that final freeze, the same expansion changes the night sky in a lonely way. As space stretches, distant galaxies are carried away from us faster and faster, until they cross a kind of cosmic horizon, a distance beyond which their light can never reach us again. One by one, the galaxies we can see today slip past that line and disappear. Given enough time, a civilization looking up would find nothing but their own galaxy in an otherwise black sky, with no sign that anything else had ever existed. The rest of the universe would still be out there, but permanently out of reach and out of sight. It isn't a violent end, and the universe itself survives. What ends is the connected, crowded cosmos we know, replaced by separate islands of light that can never find each other again. The Big Rip. This scenario asks what happens if dark energy doesn't stay constant, but grows stronger over time. If that pressure keeps rising, expansion doesn't just carry galaxies apart. It eventually overpowers everything that holds matter together. First, the galaxies are torn away from one another. Then, solar systems come undone as planets are pulled off their stars. In the final moments, the force reaches inside atoms themselves, pulling apart the particles that make up all matter, including the matter in living things. Unlike the slow fade of the Big Freeze, the Big Rip has a clear and violent finish. Space itself would be stretching so hard that nothing could resist it. Some estimates place this tens of billions of years away, though it all depends on the true nature of dark energy, which we still don't fully understand. The Big Crunch. In this scenario, the process runs in reverse. Instead of expanding forever, the universe could one day stop growing and begin to fall back in on itself, pulled together by the gravity of everything it contains. Galaxies that once raced apart would start rushing toward one another. The night sky would heat up as everything squeezed closer, stars and worlds colliding, until all matter and space collapsed back into a single blazing, incredibly dense point, close to a mirror image of the Big Bang. For this to happen, gravity would need to win out over dark energy. Current observations suggest expansion is speeding up rather than slowing down, which makes the Big Crunch look unlikely based on what we know today. But our understanding of dark energy is young, and if it ever weakened or reversed, this ending could return to the table. The Big Bounce. This idea builds on the Big Crunch. Suppose the universe collapses down to that single dense point. But instead of ending there, it rebounds, exploding outward again in a new Big Bang. In this picture, the cosmos isn't a one-time event, but part of an endless cycle: expand, collapse, bounce, and begin again. Each universe would be born from the remains of the one before it. The appeal is that it removes the need for a single mysterious beginning, replacing it with a rhythm that has always been running. The difficulty is that we have no proof a bounce can actually happen, and the extreme conditions at that collapsed point push our physics past its breaking point. It remains one of the more speculative possibilities, and one of the hardest to test: proton decay. Not every ending is dramatic. This one works slowly, from the inside, one particle at a time. Protons are among the basic building blocks of every atom, and for a long time they were assumed to last forever. But some theories predict that even protons very slowly fall apart, over time scales so vast they make the current age of the universe look like a single instant. If that's true, then long after the last star has died, ordinary matter itself begins to dissolve. Planets, dead stars, and any leftover material would gradually crumble into simpler particles and faint radiation, leaving nothing solid behind. It's a slow, patient kind of ending. No collision, no tearing, just the gradual disappearance of matter as we know it. So far, experiments have never actually caught a proton decaying, which keeps this possibility open but unproven: black hole evaporation. Far into the future, long after the stars have gone out, black holes end up as some of the last great objects left, having swallowed much of the leftover matter. For a long time, it was believed black holes could only grow. Then, physicist Stephen Hawking showed they very slowly leak energy at their edges and shrink, in a process now called Hawking radiation. Given enough time, numbers so large they are almost impossible to write out. Even the largest black holes evaporate away completely, fading into a faint drizzle of particles and light. When the final black hole disappears, the universe is left with little more than scattered radiation drifting through empty space. This is often seen as the true final stage of the Big Freeze, the moment the last major structures vanish for good. Vacuum decay. This is the ending that could arrive with no warning. It rests on a strange possibility: that empty space isn't sitting in its most stable state, but is instead resting in a kind of false calm, like a ball parked in a shallow dip partway up a hill. If somewhere, at some moment, a tiny patch of space slipped down into the true lowest state, it would form a bubble. That bubble would expand outward at the speed of light, rewriting the laws of physics inside it as it grew. Everything the bubble touched would be changed instantly and permanently, and almost certainly destroyed. Because it spreads at light speed, there would be no way to see it coming. No signal could travel ahead of it to warn us. It might have already begun somewhere far away, or it may never happen at all. That uncertainty is part of what makes it so hard to rule out: the big splat. This idea comes from some of the more experimental corners of physics, where our universe is imagined as a single sheet or membrane floating in a space with more dimensions than we can see. In these models, there could be other universes on other sheets nearby. If two of them drifted together and collided, the crash could wipe the slate clean and trigger a fresh Big Bang. Our entire cosmos would end not from within, but from an impact with something completely outside it. It's a striking possibility that everything we know might be just one layer among many, and that our beginning and our end could both come from a neighbor we can never detect. This is among the most speculative endings of all, far beyond anything we can currently test. But it points the question in a different direction. The universe may not end alone.